Hi, everyone. Thank you for coming today. I am really excited today to introduce Aris here. He is a senior machine learning engineer at Credit Karma. So lots of data there, as well as needs to figure out answers based on that data. And he is going to talk to us today about machine learning powered with ZIO and Scala. This is a talk that I'm very excited for personally. I think machine learning is something that a lot of us are interested in and are either doing or doing more of, but a lot of the resources are either in Python or maybe not really functional. And we know there are benefits to using functional programming, but maybe we don't know how to use that along with machine learning. So I think this is a really exciting opportunity to hear about that. And Aris has also been an early user of ZIO from very early on, so has gone through a lot of the iterations of adding the environment type and Zlayer and lots of fun stuff like that. So with that, let me hand it over to him.
Thank you, Adam. I appreciate it. Hello and good morning, folks. My name is Aris, and what I hope to talk about and share with you today are kind of the problem solving the benefits of architecting your application with ZIO and Scala. And from there, seeing how, if you have to make model-driven decisions, how it's really easy to do that, and how to actually incrementally add these powers. So with that, I'd like to move forward. First, just a little bit about myself to also inform a little bit of just the experience I have and where I'm coming from to speak to this. Again, my name is Aris, and I'm a machine learning engineer at Credit Karma. And these are opinions of my own, although they are informed by practical work I've done. Personally, I'm a functional programming enthusiast. I'm also interested in different types of data analysis, machine learning stuff for a while. And in a practical sense, I've been using Scala for a number of years in production, and ZIO for a couple of years. And now in my most recent projects, we've been using Google's data flow system, which is sort of like Spark, with the ZIO library, not to be confused with ZIO, to drive our batch recommender system. And so in a practical sense, I've seen what it's like to produce billions of model scores daily and to help serve those to millions of our users. The important part about this is I'm coming from a perspective of saying, like, we're actually driving revenue in production, meaning if anything ever breaks, which, you know, it has happened before, you know, we lose money. But the great thing is in a very real sense, we've been able to do a great job with Scala and ZIO, not only just driving, you know, value solving problems for the business, but also actually onboarding engineers. So it's great that we have you know, new team members who join who are smart people, but in a practical sense, we've had engineers join who have never worked in Scala, have not even thought about what this functional programming really is, and certainly have never touched ZIO. And we've onboarded them, and they've become productive, and so forth and so on. So from a practical perspective, that's kind of where I'm looking at things. And then also from the ML side and the mechanics of that, a lot of what our work is doing day to day is in Tensorflow. We're loading models in memory with Tensorflow Java, and a bunch of different models from scikit-learn. Those models are saved in the format of PMML. We use the wonderful JPMML library. I also want to preface this that if you're hearing about data science, you're hearing about AI or machine learning, there are broadly two faces to this coin in industry. So what you'll typically hear about, whether academically or so forth, is really about the modeling side. That's frequently called data science or data scientists. And those are the people who are typically building the models. They're also typically involved in experimental design, but basically building models and evaluating those models, you know, that artifact, that thing called a model, that is typically being done, or at least being driven by them. However, a model is only useful to a business, to an end application, as we'll see, if you use it. And so that's going to be the primary focus of this talk here, is saying that, hey, we actually have to use these models to solve business problems, and then also like to conduct experiments to see if we're getting anything out of these models. Frequently, you'll just try a model and realize it has a negative impact or maybe none. And so that's kind of what we're focusing on here. And again, in the space of what's called machine learning, we're going to look at mostly supervised machine learning. That just means as opposed to unsupervised or maybe reinforcement learning or other ideas. But basically the idea is we're going to get in some input, let's say a user, and we're going to predict something. In today's case, we're going to be predicting the sizes of t-shirts. Now, the important point here is that, you know, machine learning, models, and so forth has become extremely popular in the last 10 years. Neural networks have become also really popular in the last 5-ish years. But the bottom line is the mechanics, as I will demonstrate, are really complicated. There's a lot of innovation. Let's call it innovation. But ultimately, there's a lot of just complication, especially if you are trying to use these. We'll speak to that. Now, something I want to just make abundantly just clear and obvious is that, you know, writing software and making software systems is already something that, as programmers, as a discipline, it's barely engineering. So like writing software is already hard, right? If you've ever had a bug, if you've ever had a problem with any program in your life, application in your life, you can tell that it's hard overall. Now, if you are also adding in models and making model-driven decisions like the ML stuff, you are going to have a whole just universe of problems that you would have never had if you didn't use models. And I want to speak to those here because these are real problems. These are not just niggling, you know, annoying things here on the side. They can become very central. So a few of these, for example, is, you know, let's look at like model technologies, as in most of the time, although many of us have done this, you know, you can like prototype a machine learner and build algorithms with some handwritten code. You typically import a library, right? That's your model technology. You also have, of course, all these different model learning algorithms. So if you even use this technology like scikit-learn, they've got a big textbook, they've got, I don't know, 100 different learners in there. So those are different learning algorithms. For each one of those learning algorithms, there are different ways of turning some knobs, you know, inputs to the algorithm. And those are called hyperparameters. Another layer of complication. And then, you know, there's funny thing about like model refreshing. So for example, in the real world, it might turn out that as you're predicting something, you know, usually recommending products to users, it is the web after all. We're oftentimes doing this. But you'll see that the predictions these models are making eventually go bad. Now, that's funny. Have you ever written code that just goes bad? Usually not, but with models it does. And you have to like refresh them on more recent data. That's just a practical concern that happens all the time. And then separately, you've got the idea of just the design of the model from the ground up, such as, is this model actually working? Is it actually a regression, like producing a model? Is it doing a classification? Like, is it saying red, green, or blue? Or is it t-shirt size, small, medium, large? You have all these other like amazing problems, such as, you know, time traveling features that you can just track yourself into like nonsensical model predictions. You have all this concern about the input to your models, like are you having categorical features? Are you having real numbered, real value features, ordinal features, discontinuous? There are all these things that if you didn't think about models at all, if you didn't know what a model was, you wouldn't have to think about this. And again, I remind you, all these concerns and complications are on top of the complications of just having software running. I'm not even talking about that very much right now. So first step is the model technologies themselves are complicated. So I'm going to just speak to this for a moment, and I'm going to assume that if you have a model, like this actual artifact, bytes on a disk somewhere, I'm going to just, for the moment, assume that we're actually going to read this model, you know, and actually deserialize it and load it into memory on the JVM. So that's a simplifying idea here. We'll see in the future, we don't even have to think about that necessarily. But that's a good way to go, right? If you have a model, load it in memory, use it. And for example, there's a lot of ways of doing this. There are a lot of different models and a lot of different technologies that will get these models into the JVM, such as probably the most popular library out there, written in C++ and then usually used from Python, is scikit-learn. And it's very, very common to save your model in the format called PMML. That's called the Predictive Modeling Markup Language. It's like an XML file that represents a model. Model, by the way, as we'll see, is just a function. It's just a program. And there's this amazing library called JPMML that lets you do that on the on the JVM very easily. And then there's, and so the PMML is great for, it supports neural networks, but there's a more modern standard for neural networks called ONNX. So if you're on the neural network train, maybe use ONNX, and then you can just use the models directly as well. So if you have Tensorflow, you can actually just save those Tensorflow models as protobuf, and then read them in with the Java API that exists. Android is Java. PyTorch has gotten Java bindings. XGBoost works really well. SparkML, again, you can use the models directly. You can also save as PML. Anyway, at some point, your eyes will glaze over. You'll realize there are many, many options. There are many, many technologies. At the end of the day, some people took this book of math, wrote it in some language, and they used a computer to perform this. So it's a model technology. The important point here, though, is that all these different toolkits, potentially and basically practically, they work differently. They're different. They're not the same thing. That's complicated. Okay, once we get over the whole import this library, import that library, the real modeling, like the mathematical part that's on paper and pencil, really, that's complicated too, as you might not be surprised to learn. And there are actually algorithms like core learners, and there are even meta algorithms. And just to speak to a few, you have probably heard about neural networks. There are deep neural networks, maybe more shallow neural networks, actually logistic regression. Those are multilayer perceptrons, feedforward networks. We also have like cool things like recurrent neural networks that are really cool for, you can even translate languages from one to the other. You have cool things like convolutional neural networks for images. And then you have all these other non-neural network technologies, such as support vector machine, logistic regression, linear regression, random forests, great user trees. Then you have these meta algorithms that can actually take your basic learner, like and then you can use things like stacking, vertical and horizontal stacking, ensembling, boosting. Okay, just saying a lot of words at this point, but to anyone who's worked in the field or talked to your favorite practitioner, you'll realize that it's complicated, and all these algorithms, they work differently. At best, your interface is, are you giving me a regression or are you giving me a classification? Right? But internally, they all work differently. Now, if you've been lucky enough to pick a technology and pick a learner, like your model learning algorithm, you still have hyperparameters. You don't just have one thing, you have to tune it and try learning different models to see what happens. So if we just look at something like, deep neural networks, okay, so what do you have to worry about that? How about the actual layer architecture? So you've heard of deep neural networks. They're deep if they have more than a middle layer. So input layer, 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 output layer. How many neurons are in each point? What are the inputs? What are the outputs? What about the actual activation functions inside? You've heard of like ReLU, leaky ReLU, sigmoid tanh, all these other things. Then with backpropagation, to actually learn these weights on each layer, you have to use something, gradient descent, popular thing, SGD, momentum, atom, RMS prop, whatever. There are many, many things out there. And then there's even this cool thing called dropout, some percentage dropout. Look, the bottom line is, I'm hoping to convince you that things are very complicated, different hyperparameters for the different learners, all work differently. This is just stuff that if you didn't use models, then you wouldn't have to worry about this at all. So again, complication, ways of making your software not work. Now, there's complexity that is unnecessary. There's complexity that is like irreducible. Like you have to deal with complexity. So at the end of the day, you have to control the complexity. You can't just like delete it. usually not make good software or not make good systems. So the point being here is that using Scala, especially with ZIO, is a great way of controlling complexity. And that's actually the most important part here, and that's what we're going to speak to today in a very practical sense with code examples, with a toy example. Now, again, if we wanted to speak in memes, this is kind of a meme. We've all seen movies that show like some genius dude writing formulas on the blackboard. I don't know who actually does this. I don't convince it's a joke. But if your code ends up looking like a scattered bunch of just learners and model metrics and things, basically, if your code looks like this, no. That's what I want to say. Is like, really, no, you don't want this. This is not. Does not mean that your code is particularly clever. It does not mean that you've done something particularly smart. This is basically the equivalent of having written chaos, because we cannot interrogate this code easily to understand if it's even correct. Also, the only thing we know about programs is that we have to modify programs. And if your code looks like this, you cannot successfully modify this program, especially in a team, or someone else jumping into your code. I would prefer to have code that looks something like this. And we're going to talk about this, this little microservice, this little server. So let's just say yes. And even if you don't know much about Scala, if you don't know anything about ZIO and you're a little confused here, you can kind of squint, look at this, and we'll talk about this at length. But this is something that you'd rather strive for rather than the previous chaos. Now, again, we talked about there is complexity. Sometimes it's irreducible. How do we control it? So, look, at the end of the day, you may or may not know a lot about functional programming, but it's kind of these techniques from functional programming is what ZIO is helping us with, within the power of the Scala compiler and the language. And ultimately, for example, what we have is a few things here that are going to be really helpful are pure functions, the ability to push in dependencies, and to be able to control effects like, like threads, concurrency, and input-output. So concretely, like pure functions are super helpful because they are basically just like programming with Lego blocks in a very nice way. So if you've ever built anything with Legos, imagine if you just didn't like this Lego in the middle of your little cool spaceship because you wanted to change the color. Well, that's like a segment of code, and you could easily remove this Lego, put in this differently colored Lego, or different shaped Lego even. But you know that this Lego is, for example, it's the right color because you can see it. So, and also, just because you change this one Lego, it doesn't ruin everything else. So that metaphor is very much the idea of local reasoning. Just this little small section of code, if I look at 20 lines of code, but those 20 lines of code could interact with any of the other 10,000 lines of code, that's a nightmare. And that does happen with a lot of procedural code that ultimately has like a global state. So that's called like local reasoning. I would like to only look at 20 lines of code at a time. I don't want to actually memorize 10,000 lines of code to understand what these 20 lines of code are doing, right? That's kind of the cost of having a human brain. This dependency injection, for lack of a better term, is something that, in functional programming, ZIO has something called Zlayer, and it's going to be secretly your reader monad. You don't really need to know what that does, what that means, but you'll just know that somehow, somewhere, you're able to get your cool dependency, your cool, useful piece of work comes to you. And that's going to be where we like get our models and our cool model technology from. It's also going to have like a very nice uniform interface. And as we'll see, it may or may not even be a model, right? So we'll see about that. And also, when you are writing software, we actually have all types of complicated things we can do, such as if you use the JVM, you have probably had an exception thrown. That's an effect there. Have you ever tried to run a bunch of processes at once? Let's say a bunch of models, run them all. You can do that, but frequently, if you're actually manually manipulating threads, playing with threads, pausing threads, doing things like that is perhaps the best way of ruining your application. But a lot of times we need to do something to that effect, right? So being able to control these effects, which is what ZIO does, eventually you'll see that it gives you superpowers. And we'll look at that. Now, here's my basic thesis here that I hope to convince you of, or at least influence you a little bit, is the idea that ZIO Scala gives you the ideal tools to architect an application, to be able to actually use, machine learned models really in the real world. And I mean every word of this here. So step one is, what do we mean here by when we say real world? What happens in the real world? So step one in the real world is, I'm going to speak to my experience, is that this is a production system. This is not a homework assignment that you went on Coursera and you played with MATLAB or Octave and so forth, like I did back in the day. Like, this is a production system that if it doesn't work, money is lost. If enough money is lost, you don't have a job, you don't have a business running. So this needs to work. Step two is that you probably work in a team of people. It's not just you by yourself doing, oh my God, really clever things. No, you actually have to write code that other people can pick up and modify and fix and improve and change, like, concurrently. Other humans are thinking and doing things at the same time. You also need very good performance. Like, one of the reasons people like the JVM is because it's fast. Right? It's not just like some raw Python function or something like that, like pure Python. Also, the real world, your models are never born perfectly. They're never learned perfectly. You have to iterate on the model. You have to change it. We're gonna see that presently. Also, the vast majority of your application is not, it's not the model. That's a small percentage here. You actually have to modify other parts of your application also in parallel. And again, you also need to test parts of the application. You people have to walk in, change code, test your code in part or in whole. So the bottom line here is, forget computers and technology. It's all about better, faster, cheaper. Remember that. Better, faster, cheaper. For the engineer, for the business. It's better as in your code is more correct. Faster as in it's quicker to implement. And cheaper as in it's actually easier and less expensive to modify your code and maintain your code. So better, faster, cheaper. That's, if there's anything you remember from this talk, please remember that. It's better, faster, cheaper. Now, one intuition I want to give you here is that a machine learned model is a pure function. And that's actually pretty cool because that says that we have a natural match between kind of using something like Scala with ZIO, which you don't even have to know it's functional programming, but it is, and machine learned models like we have. I work with PhD physicists and PhD computer scientists. Well, physicists, they don't really care about functional programming that much, but it turns out that it is a match made in heaven. Now, again, models are pure functions in a very concrete way because you're just mapping inputs, which we usually call features in the ML language mostly, and into an output range. Those are called predictions. So again, we'll see here that if I have a user I know is age, weight, height, sex, et cetera, things like that, I'm going to come up with a prediction to be like, your shirt should be small, medium, large, extra large. You can intuitively understand that kind of makes sense. And again, what makes a pure function? Totality, deterministicity, and being side effect free. So concretely, that means that the function, if function is total, if for any input you get an output, it doesn't break or throw a side effect. Now in the real world, depending on the model, may or may not be totally true, but with ZIO you can make them total very easily. Deterministic just means that if you ever put the same user into this model, you get the same t-shirt size out. So the predictions are always the same. Yes, by far and large, that's what models do. If they did random decisions, you would not be very happy with this model. And also side effect free, meaning the only thing this model does is it calculates a value and then it returns that. It does not interact with the outside world. So for the balance of this talk, I'm going to have something to concretely talk about, and I wanted to have a small microservice application called Size My T-shirt. And so imagine we're part of a business, Macy's or some online application, but basically we're selling T-shirts, and the basic flow is a user picks a design of a T-shirt, and we know all this information about this user, and we actually suggest the size of this T-shirt. And we have two types of suggestions. We have standard T-shirt sizes and tailored T-shirt sizes. So again, this is a simple toy application, not anything complicated, but it's useful for us to understand here. We know, and by standard we mean small, medium, large, extra large. By tailored, imagine we have we somehow know the neck length, we know the trunk size, we know arm size, waist size, like a tailored T-shirt. And the point being here is, this is just a way of like getting you to think about the idea that yes, if we knew that this user is 2 years old and so tall, probably wants an extra small shirt. If the user is an adult and 250 pounds, maybe he needs an extra large shirt. You can tell that just with your mind, but also a machine learning model would probably pick that up as well. And again, the tailored t-shirt is just an extra layer of like more complicated. And so in machine learning models world, we would usually say that small, medium, large, that's like a multi-class classification. And if we are actually producing numbers to be like, your neck is this many centimeters, your trunk is this many centimeters, that's like regression, so in fact, multiple regressions. So let's work with this example. Now, I'm just going to show you a couple domain model things here. Nothing complicated, but again, we're going to be seeing these types in the application. But the only thing to keep in mind is, hey, we have this user, and frankly, it's user features. And again, like I said, if you're interested in sizing a t-shirt for a user, you know, ID is kind of like an ID, you use that. But, you know, let's say your height in meters, your weight, your age, sex, fitness level, some number, whatever that means. But again, this doesn't matter so much, but imagine we had just a bunch of measurable things that would actually influence probably what size t-shirt that user wants, right? So it should not be surprising. Also, based on that user feature, we're going to be predicting t-shirt sizes. And as I promised, I said we're going to have two types of t-shirt sizes. I have a small algebraic data type for t-shirt size. One is a tailored t-shirt size. No, that's a complicated one, right? It's tailored. It's for the trunk in centimeters, the waist in centimeters, neck in centimeters, chest, whatever. The idea is it's more complicated than a standard t-shirt size. Standard t-shirt size, again, is just like small, medium, large, extra small, extra large. And again, the standard t-shirt size is probably going to be modeled as a multi-class classification. Tailored t-shirt size is going to be, you could think about it, it's probably more complicated, and it's going to be real numbers for all those measurements, right? So it's going to be a regression. And so here's a quick sketch of what we want our application, my size my t-shirt microservice to look like. And if you hopefully you know some Scala, but if not, that's okay too. Hopefully what you're going to notice here is even if you are walking in here from just having written Java or Python or anything, this should hopefully be mostly understandable, but I'll go through this real quick to explain what this application logic is. So the first thing that you're going to notice here is that we have, this is actually a value. This is not actually some def. This is not what would be called procedural code. This is not actually modifying memory and doing computations directly. In fact, what this is a value, you know, like an int or a string. Oh, it's actually a more complicated data type, but it is actually a description of a program which will be run later. Now, this may be a little bit tricky. You may not understand exactly what that means. I didn't either in the beginning, but just believe me. And we have types in Scala, and so this is of type ZIO with three type parameters. Now, this just says that this will run in any environment. So that's kind of saying that's kind of an input here. We'll see what that means. And it can return an error of a throwable, so like an exception. And it will return, in this case, this server will actually return a nothing. Now that's a little bit crazy because nothing is what's called a bottom type in Scala. It's a bottom type, meaning that there are no values of type nothing. So what does it mean for me to have a program that returns nothing? Oh, it's an infinite loop. Cool. We actually want an infinite loop because this is a server. This is going to get requests, figure out sizes, and then send responses. So returning nothing is actually what we want. And just by looking at the type signature, we know that this might fail with a throwable. Yeah, it's JVM. But it should return, it will return nothing. And then this is what's called a for comprehension. And it's not so important at this moment to understand what a for comprehension is. It's a little bit of syntactic sugar, but it helps you kind of embed, even if you're using effect monads, which is what ZIO is, you can still sequentially do work like you do in an imperative program. So if you've written any programs in most programming languages, you like to do one step followed by the next step. That's all we're doing. Now, step one is imagine we have some magical way of getting a request, which is a request. Let's say that for that request, we get the, and again, let's pause. How you get the request, it could be HTTP, it could be, some REST API, it could be some RPC call, it could be really anything. We're not too worried about that right now, but you can tell that it's a getting request, some side effecting action, it just happens somehow. Now, for a request, imagine that has some useful information in there, and we want to get the user features for that request. So we have another function, maybe it talks to a key value store, Redis, Bigtable, HBase, a database, I don't know. It does somehow, for this request, it gets the user information. Remember those user features we said? And then these two bolded lines, this is what we're going to be looking at a lot, because this is the meat of what we're concerned about. We're going to be getting two predictions. One is a standard t-shirt size, one is a tailored t-shirt size. And that's going to happen somehow. And we'll speak at length. And then once we have those two t-shirt sizes, we're going to send a response back to whoever asked with this send response function. Again, these are just kind of like abstract functions that exist, but with the request, with the standard size or the tailored size. And we'll see this yield. We're yielding kind of nothing. We're yielding unit, which is trivially just a unit. Doesn't mean much. Like think of it as void, sort of. And then we have this dot forever. And that's like your first clue of like we're doing something kind of crazy, but that's called a combinator. That comes from ZIO, and it just says that, these steps that we have over here, do them forever. Notice that I didn't do something like while true. I didn't have a procedural construct there. This is a declarative functional combinator that is very highly compositional, and that's just what it is. So hopefully, if you're looking at this for the first time, looking at this and so forth, this is fairly straightforward to read. Now, the first step is really what you would like to do is this application, you'd like to be able to have something that runs with no models, despite the fact this whole talk around having machine learned models, right? Now, if we were to believe anything from Google, they have a fairly famous paper called Hidden Technical Debt in Machine Learning Systems. Now, that's a paper about all the crazy, terrible things that can happen by using machine learning models in your computer systems. And one thing you learn from it is saying that, like, hey, if you can not use machine learning models, how about you don't use a machine learning model? And for the purposes of this discussion, I want to show that we can actually abstract away. We can just not think about machine learning models. In fact, we can start a system without a model, and then we can later incrementally add models. And the reason I say that is just think about this. What does Size My T-shirt service have to do with models? T-shirts, machine learning, math, things like that. Nothing is the answer. So it would be great if we can actually architect our server application, this microservice, to be agnostic, to not know about models, that'll somehow get, it will somehow give you a small, medium, large size, it'll give you a tailored t-shirt size, somehow. These two functions will exist, they will exist somehow. And at first we just hand write a heuristic, right? Like some code that does something and returns something useful, but written by a human. And this can also be an opportunity to collect labeled training data. So again, if a user is actually using our system, says like, oh, I like this design. Oh, they recommended that I have a medium. The medium's good. Or if they say it suggests an extra large, actually I just want a large. We can those sizes are called labels, and the users are observations. So this is an opportunity to actually collect the data. Now we're going to start moving into some of the more ZIO specific stuff. And the ZIO specific stuff is something called, how do we push it? How do we, basically program to an interface? But how do we do this in a way that is easy and compositional and works really well? So we have something called this fairly new addition that I like to ZIO called ZLayer. And ZLayer is a way of being able to package up your dependencies. And we're going to see a lot of this. But remember, we saw in the previous slide, we have this compute standard size function and compute tailored size. And we've been seeing these functions a couple times. They were in bold. But basically, we're going to look at this as being a module or a service, and somehow we're going to be producing a bunch of instances of this capability. The capability of computing a standard t-shirt size and computing a tailored size. And as I promised, let's first do it without any kind of model. We'll do something handwritten. And up here, we also have this little bit of stuff here called has t-shirt sizer.service. So whenever we look at t-shirt sizer, we just know that there's a dependency on this service here. This service being the ability to have two of these cool functions that if you pass in a user, we return a standard t-shirt size or a tailored t-shirt size, or we fail with like a JVM exception. So just remember, standard size, tailored size. Now, we're going to create our first Z layer. And as I said, we're going to not be worried about the model business right now. We're just going to have some type of manual model. So we're going to compute standard t-shirt sizes and compute tailored sizes manually, somehow. And so if someone told me that I had to manually calculate small, medium, large, extra large, whatever, I'd be like, hey, I've heard about this thing called BMI, the body mass index. So how about I just calculate the body mass index and then for the standard size idea. And then I return a size and I'm like, if you're this BMI or less, you're small. If you're under 25, you're large. Otherwise, hey, I'm sorry, medium, else you're a large. Cool, right? And remember the BMI function is like weight divided by height in meters squared, but divided by is actually dangerous. Remember, like if you divide by 0, if you're being sloppy, it'll actually throw a JVM error. It'll be like some type of error, can't remember which. But I actually just do something cool. It's another combinator called catch all, like catch all the errors. I'm just going to give you a BMI of 24. Fine. You see this little IO thing. You'll see a lot of UIOs, IOs, ZIOs, but those are, again, we're just building up a data structure that describes our program. That's what we're doing here. And then, but for the tailored size, let's imagine that tailored sizes, boy, they're complicated. So we do know what the average tailored t-shirt size is. I just wrapped that in the companion object, AVG, average. I throw up my hands. I'm just going to return the average tailored size because we would like to have a useful model, especially for tailored t-shirt size, but we don't have one yet. This is what we're doing. And so what we're going to see here is actually a couple things. Oops. We're going to see a couple things here, and ultimately just a small change to our application code. The one time we're going to change it, and that's kind of the architecture of it. And then we're going to see how to use that architecture. So again, everything has a cost in life, and I'm going to share with you what the costs are to have this ability to push in the dependencies. So looking back at our size my t-shirt microservice, we're going to see that, okay, I changed a couple things. First off, I now have that t-shirt sizer service where it used to say any. Now it says that if you want to run this program, you need to give me a t-shirt sizer. That's what that means. That's an input to this description of a program, this ZIO. Now we see this thing called ZIO.accessM. That just means that I know that I was passed in a t-shirt sizer. I want to access the t-shirt sizer. And we have this env, that's the environment. All right, not so bad. And then where we used to just have compute standard size and compute tailored size by itself, you see that we take the environment, we get the t-shirt sizer, and then that's what gives us the ability to compute standard size. Cool. And of course, you could wrap this in a function, get rid of some of this end.get stuff. But the bottom line is I'm being explicit, and you're seeing, I'm showing you what you're paying. You are paying this cost, but you're going to get a lot of mileage out of it. And now once we've said that we're using ZLayer, well, we want to actually run this in a driver program. This here is a driver program. Size my t-shirt app extends ZIO.app. And so what you're going to see is you have to like construct these layers. Remember how we just wrote a t-shirt sizer.manual. So cool. Give me the manual sizer, not model based. It's going to be done manually as I showed. And then you take your actual application, which is at the top there, size my microservice. And before you run it, you have to give it the input, which is called the layer. The layer is t-shirt sizer.manual. and then you just, return exit code to, to your command line. That's it. So you now have actually taken your size my t-shirt microservice. You've added the ability to easily do this standard t-shirt size and tailored size in a way that you're going to see that is highly, highly, highly flexible. And we're going to see a lot of iteration on this. And to be completely open, talk like an engineer, you did pay a cost. And this might be like, oh, what did I do? But you'll see that the cost pays for itself over and over. Now, in the real world, if we want to build a model, we actually have to collect a training data set. So part of all types of real systems that actually have to do work with machine learning models is you have to do logging. You actually have to log, hey, this user or this observation came in, like this prediction request came in. And then we also had to, we did inference on some type of model. And then here's what our inference was. This was our guess. This was our prediction. So one way or the other, you have to do this. And logging, is a side-effecting operation. And why does that matter? Now, let's step one. I'll go back to this whole thing about a side-effecting operation, the fact that it might be a time limit costly operation. But the first question is, what does size my t-shirt, the microservice, the application, those 5 lines, what does that have to do with training data for a machine learned model? The answer is nothing. So those are separate concerns. We would really, really like to keep them as separate concerns. There might be a temptation to write sloppy, terrible code and just write a bunch of code and overlay it on top of each other. But let's not do that. Let's have an architecture that allows us to do this other stuff like logging without affecting our application code. So what we want to do again is we want to log what sizes the user selected, and we want to log also who the user was, with all the user features, and we're creating a training data set. So what we're going to see here is we're going to use Zlayer again and add what's called a vertical dependency on something we're going to call inference logger, because we made the inference, we're logging that, and we're going to add that dependency on inference logger to the t-shirt sizer. So t-shirt sizer will need to know how to do a logging operation. And again, this logging operation can be as complicated as need be, because in the real world, you may not have all the user features. Somehow you may actually have only user ID, and you need to enrich that ID with all the user features or more additional features to create a really good data set to train a model. And if you ever want to be best friends with your local data scientist, doing all these nice things that you can will not only make you friends, but it'll make better models. Hopefully these models will drive business value. You guys will make money. You'll be happy. That's what you want to be doing here. So, however, just willy-nilly adding latency to your application, all that is typically not a great thing, but I have good news. We're able to handle all those problems. So let's look at another module called inference logger. And what we're going to see here is ultimately it has one capability called log. And again, we're logging observations for the purposes of machine learning. And what we see here is ultimately we're going to have users and sizes. A user, again, is the input feature vector, like it's a user, height, weight, all that stuff. And the size is the target of the model, what we usually say. So do you want to have, and this is a t-shirt size. Remember, we have 2 types of t-shirt sizes, small, medium, large, or that custom tailored one with the centimeters of everything, the fancy one. And what we're also going to see here is, okay, so if you can log, we want to have 2, let's call them like constructors, 2 ways of creating layers. Frequently, we call them live and test, and production and like unit testing training. So if we look at the live one, and again, this is a stub, this is where your actual business logic would go. But you see, we're trying to define log. It's going to return a UIO of unit. UIO of unit is usually a code that if you have a pure function that returns unit, which is kind of like void, think of that, kind of. That just means that something happened, and it probably was a side effect. It probably wrote something somewhere, read something somewhere. Now, in this case, I say triple question marks, and I'm not going to give you the mechanical details here. That doesn't really matter. But imagine you were writing to pub sub or Kafka, or putting a row in a database, something. And it's, like I said, even if you're doing enrichment, that could even take a little bit of time that would add latency to your application. The cool thing is here, like in your live production thing, you can easily write out or do even a little bit of enrichment, and you can even fork it off so this returns back immediately. And you don't like wait a second every time you log on these operations. So that would be like your production world, something like Kafka, something like PubSub, perhaps. Or in the test cases are really nice because it helps you kind of immediately wrap your mind around what I'm talking about. But if I'm logging a user and I'm the input user who wants a prediction, and I give you back the actual prediction, in this case, our test log is just a print line, right? We're just going to print to the screen. And it's going to be, I logged this user, whatever, with all the user features, and this size. There you go. So this user had a size small. That's cool. And you'll see here, this is UIO. Just means it cannot fail. Unexceptional IO. Don't worry about that too much. Again, you're going to see some of these IOs and so forth. But remember, everything we're doing here is, it's not actually procedural. It's actually, you're functionally building up a data structure to describe a program that's going to later be run. And now, here's what the t-shirt sizer looks like when it uses the inference logger. So remember, we saw something like this before, an inference logger. This is what gives us the ability to compute a standard size, compute a tailored size. And let's look at that. So now we said that we require an inference logger. So that's up here. And we have this little helper function here called Zlayer from service logger. That's the logger we just talked about in the previous slide. And if we look at, let's say that we're just going to look at the same two pieces of code, that manual ability, like the BMI thing, and then the average Taylor t-shirt size thing. The cool thing is remember I talked about, hey, this is this for comprehension thing. It's very much just like writing line by line code. Well, the cool thing is, look, I just wrote logger.log, and you see it's just one new function composed. And this is actually composing a function. It's not procedurally doing an imperative operation. It's actually functionally doing an imperative operation. So people talk about composing a function. You have f of x and g of x. It's actually f of g of x. Even though it looks like you're doing f of x and then you're later doing g of x, you actually know it's actually one after the other here, or one composing with another here, instead of two completely different operations happening. Now, that may not mean anything to you. That's actually fine. The cool thing is the syntax here with the for comprehension makes it such that you just do one thing and then sequentially the next thing happens. That's all you need to think about, which is usually how you think about your programs in the most common way. Lovely. So again, now what we're going to see here is you're going to hear me saying this again. Look at our application. Remember we said that our application should not really care about logging, should not care about modeling. Well, we didn't change the application at all. We didn't. We paid for that Zlayer machinery once. And now the way that you're actually able to push in this new logger with this t-shirt sizer is down here. It's the layers that are slightly changed. So we say, hey, feed an inference logger, feed it into a t-shirt sizer, the manual one with logging, and everything else is the same. That should be slightly exciting to you in the sense of, like, we didn't change the application code at all, but we gave it like a really serious new power. Not only do we have like this manual model, but we now have also this ability to log and do really fancy logging. Again, like, anything you can imagine fits into this. And we separated the concerns entirely from the application. Third step. All right. Use the models. This is the moment we've all been waiting for, is we want to be able to actually, somehow we got some models, we worked with our teams, and okay, cool. Now, again, you're going to see me asking similar questions over and over. Let's say that our first model was built in scikit-learn. Let's say it was a logistic regression model. Okay. Let's say that you saved out, again, PMML is a very nice representation. That's that XML representation of a model, any model, basically. What does everything I just said, what do all those technologies and things and concepts have to do with size my t-shirt microservice? Again, the answer is nothing. Those concerns are separate. We would like to keep them separate. We would not like to muck around with our microservice because we want to add these admittedly useful powers. But we have the ability to do the architecture to not mess around with the microservice. So we're just going to modify the Z layers. We're going to push down those dependencies in there. And we'll show how to do that here. This is the ultimate separation of concerns. And oh, also, the one thing we're going to see here is that, like, again, in the real world, imagine we have two types of predictions. One was small, medium, large, standard predictions, and one is the tailored t-shirt predictions. Let's just imagine, like this happens actually in production, that you might have a good model for one thing, but you don't have a good model for the other thing. And we're like, that's fine. I'll show you how that works. It's not a big deal. So concretely, remember our t-shirt sizer service, the one that computes standard sizes, computes tailored sizes. Let's just say that we have now, this is where the mechanical code of loading in a model, like the bytes. There is a model that's been saved somewhere, like on S3 or on GCS or something, or on a file somewhere. That's the model path. And remember, we said that we want to pass in a logger. That's the thing we already did. But we're just going to have this function here called get LogReg model for standard. And this is where the mechanics of loading the model are here. This is where you use the great JPMML library and you read in this PMML file and it does the magic for you and it returns to you this evaluator object. And the evaluator object that says, this is what gives you the ability to do a prediction. User features, those are the inputs to the model. And this task of standard t-shirt size, that's the prediction. That's all we're saying. This is actually just Scala syntax for, this is a function from user features to a description of a standard t-shirt size. That's it. That's where all the complication, everything we said about like the model technology, the model learner, all the hyperparameters, it fits right into a function. That should be very exciting. And separately in our t-shirt sizer, we now have, we're going to load in memory. In memory, we're going to load it once, in cache, you know, do all the nice things of a standard model. User features to task of standard t-shirt size. That's just a function from user features to a standard t-shirt size. And here we're going to use this model to compute the standard size. We have one model to do a standard size. And then, however, we said that for the tailored size, remember we said our model wasn't very good based on whatever metrics, say mean squared error or whatever type of regression metrics we ran on there. Like the model was just not good enough. Oh my goodness. That's fine. We still just return the heuristic, the non-model based thing. So you see a little bit of modeling, a little bit of heuristics. That's fine. It's production. We have to do something. We have to like keep our customers happy, right? So it works. And once again, you're going to notice that on the top, the code for the microservice, size my t-shirt microservice, it is fine. It did not change. That's exactly what we want. And then the complication is we just say t-shirt sizer.logreg PMML sizer. Here's the path on S3 or GCS to the actual model file. In this case, it's an XML file. The PMML file is there. That's what it looks like. That's all you have to do. And the application code stayed the same, but we actually used a model. Wow, that's very exciting. Well, that's pretty cool. Now, the point we've all been waiting for, of course, is saying like, oh, we've got enough data. We've been working with Tensorflow or whatever neural network-based system you like because it's exciting. It is a little bit of Kool Aid, I gotta admit, but hey, we've now built some models, and you know what? Why not try these models? Let's try them out. Some people say that neural networks are a little bit overblown, but you know what? There's no need to get into machine learning holy wars. Ultimately, if you've got a software architecture that really, really easily lets you drop in models, you don't have to argue about what model is better. You can just try the model. So we just saw the one previous model. How hard is it to insert in a neural network model or TensorFlow model of any sort? Well, it's very easy. And in fact, let's say that we now have a new standard model and we also have a tailored model. It's our first tailored model. Oh my goodness. So all I said was, imagine we now have two separate helper functions, one that reads in the TensorFlow model and builds you your standard model, one that reads in the TensorFlow DNN, deep neural network model from some model path, and it reads in your tailored model. And again, triple question marks here. It's a little bit out of the scope of what I'm trying to communicate here, but this is where you put in your mechanical code that looks at a model path, uses the TensorFlow Java API, reads in a saved model bundle format, does all the ugly Java stuff, but then it loads in the model into memory. And it is a thing that knows how to now take in your user features case class and return a prediction. Like internally, the API for TensorFlow says, oh, you have to make an org TensorFlow example out of your user features, and then you'll feed in this model and you'll do these very ugly things. But hey, you're able to actually produce predictions without having to change your application code. And here's where your standard model exists. You're reading in your TensorFlow model here, like on construction time, right? Here's your tailored model, and it will live in memory. You build this the first time on construction time, and you use these models, as I said. So there you go. Now you have two models for your two capabilities, standard t-shirt sizes, tailored sizes. That's it. That's all it took. Again, we did not change our application code. And again, the only thing we changed was our dependency here. Instead of using the previous t-shirt sizer, we now use the DNN TensorFlow sizer. And you know, we're reading in a model. Like this is like you just write a model somewhere and then you're able to use it. This is exciting. Now, if you're doing all the stuff here, you want to be able to unit test your models. Well, you're going to notice that I'm going to be kind of repeating myself here. It's just another, you know, probably a manual model. Let's say that in order to do unit tests, we don't want to like go out and read models and load bytes and do crazy things. Let's say we just want the standard size to always be medium, and we want the tailored size to always be that average size. It's really easy. And let's say we also want to like log the print line, right? So again, we're going to have a Z layer. It relies on the inference logger. That's probably going to be our test logger. And then I have this helper function test service, which actually gives us the compute standard sizes. And as I just said, for the standard size, always return a medium, and then do our little logging action. And for tailored size, always return an average. This is your unit test. You're not reading in the bytes, you're not doing anything. This is just another manual model. But in your mind, you're like, this is my unit test. Again, we didn't change the application code. The only thing we changed here was inference logger.test, push it into a t-shirt sizer.test, run your unit test. And these unit tests can be done with, you know, with ZIO test or tried and true Scala test or whatever testing framework you want to use. And this is, again, these are unit testy things that still work within the design of your code. So you're able to test this in part, you're able to test this in the whole. It's very easy. And to cap this off, what if we want to do something really exciting? Let's say we want to do something like, well, here's the problem. Well, we want to have multiple models and we want to experiment with multiple models. Now, why are we doing that? If I asked you, what is the best model for a t-shirt? Like, I want you to tell me, like, produce that model. I don't want you just to theorize. I want you to write that model for me and build it for me. The actual correct answer is, I don't know. You may have ideas, you may have a bunch of ideas, or you may have a class of ideas. But ultimately, you just need to produce a lot of these models. And they might be different technologies, they might be different learners, they might be different hyperparameters, but you want to be able to just try them. And frequently, like in a real production system, like real companies, we also have like experimentation frameworks. And let's just say, imagine we have 20 models, and we're just kind of like, we're actually, we have an experimentation framework that knows how to take any user and map that user to deterministically to one of these models. And again, we're kind of using all these models, then we're going to do with the logging, we're going to do offline analysis, and we're going to see which one of these 20 models actually does the best. And if you're thinking about like your recommender systems, you're recommending real products, you really care about which one of your models is actually converting people the best, because that earns real money. So really experimenting with real models is really where the money is. And if it's hard to do this, it's hard to do this. It's hard to actually make good models. It's hard to actually drive business value for these models. But we're going to see that it's crazily easy to do this with the architecture I'm just suggesting here. You just add one line to that for computation because you're just composing in another function. Again, t-shirt sizer.service, another one. This one's called experiment-based sizer. This one's going to take in something called an experiment framework. Experiment framework is really easy. All it does is says, for a user, give me one of the many models, right? And it actually just ends up being one more line of code, just, you know, another step. So instead of using a model directly, let's say for standard size, we use experiment framework, and we select the model, that's what it knows how to do, based on user ID. So now we have a model. This thing here is a model. It's a t-shirt. It is a t-shirt sizer.service. And we see here we do selected a model.compute standard size for the standard one. And for the tailored size, very similar, selected a model.compute tailored size. Now, I'm going to repeat here. We are actually picking one of many, many models, and we're deterministically being able to pick which model for this user. That's really extremely useful for the data science organization. And again, that experiment framework, this is a toy experiment framework. But imagine here, like in the live production system, imagine what you do is in memory, you have a map of, let's say you have 20, 30, 40 models, I don't know. And what you're actually doing is you would hash a user deterministically to some hash value to pick one of those 40 values, right? And then the model, this capability called select model, all it knows how to do is it would hash a user and then select a model. And then that would be turned into your t-shirt sizer.service. And like, again, testing is always helpful. So all it does is it always just returns the actual test version that we wrote in the previous slide. Now, the really exciting thing here is people like to come up with useful, clever ideas, but if you have to change your application logic over and over and over, it's hard to do, it's hard to test, it's hard to improve. All I did now was I have inference logger pushes into experiment framework, pushes into t-shirt sizer. This is just being, these are all just Z layers. This is all just pushing down your dependencies. You haven't changed your application code. That's really exciting. Now, just to reiterate what we did here. We've talked about a lot, but I just want to reiterate. What did we do? For the same application code, for this size my t-shirt application, we started off with no models, and we were just calculating, we were just guessing based on a heuristic. Secondly, we made calculations based on one model, that logistic regression, scikit-learn, PMML thing. Later on, we were like, oh, we were able to make two models, one for standard t-shirt size, one for custom t-shirt size, and it totally worked. And that was, of course, our Tensorflow thing. And then finally, we said, we're not going to just have static models. We're going to dynamically pick models based on users, because we have like 40, 50 models. We don't know which one of these is the best model, but we're able to start, we want to start doing a lot of analysis on them. Now, we went from nothing to hyper super turbocharged with no application change. That's really exciting because at the end of the day, unless you can actually experiment and try in an easy way, you're not going to experiment and try. And we were able to experiment and try a bunch of different things, but we left our application code alone. It did one thing, it did it really well. It took requests, gave you standard and tailored t-shirt sizes, but we were able to do all these meaningful changes easily and in a testable fashion. And like I said, there are so many technologies, so many types of algorithms, so many just ways you can even mess around with the algorithms. You just have to be able to experiment. For example, imagine if we said, rather than picking one of those 40, 50 models, imagine we ran all the models, because we're just collecting data. But we can't slow down the server. Well, guess what? With ZIO, you can just spin off a bunch of fibers, like in a line of code. You can run all the models, you can run them all asynchronously, and then you can log all those things asynchronously and just collect data for the data science team. You can just do that for all the models if you just throw some computing resources at it. It's just the case that the code itself barely changes. It's just some combinators there. You can do other fancy things, such as, there are actually, a lot of times it turns out good models take more time to run. So you can, for example, if you have a few different models, you can actually race the models and see which one returns first, if that's what you're trying to do. You can also do kind of a complement to racing models. You can actually put a time limit on models. And we actually had this happen in production before, where somebody had a boosted model and he did too many rounds of boosting, like 1,000 or something. And it took so long that it killed the models. Well, guess what? In ZIO, you can actually you can put a timeout on an operation just by doing .timeout, and then just give a backup prediction. Like, we didn't have this amazing ability, and we actually blew up production. So all these things can be easily done in ZIO by doing something oftentimes, because you have all the extremely powerful combinators that let you stay on a very high level. But like I said, you basically are able to have superpowers as a programmer, because you're sitting on top of the superpowers that ZIO and Scala are giving you. And if you have these superpowers, at the end of the day, you're able to try a lot of things. You're able to discover what are the best models. You're able to discover what makes your users the happiest. And you're able to drive, drive really, get business value. At the end of the day, it will earn you money. And again, there's actually still future improvements I can make with this. I actually think the main server should be modeled as a Z stream, like reading from a Kafka topic, something like that. I think modeling as a stream of like infinite stream of requests coming in and then responses coming out models it better. Unfortunately, I just ran out of time. I think other cool things you could do here would be like live reloading of models. Remember I said that models need to be refreshed? Well, it'd be nice to have like a zero downtime way of simply saying like, hey, we're logging out all these predictions based on some, some metrics, whatever those metrics are. There are many: precision and recall and F1 score, many things. Ultimately, we could say we would, if the model ever goes bad, we could listen to, wait for a new model and then live reload it, part of the stream. That's pretty cool. And the other big assumption I had was that these were all models in memory that I said, TF Java or JPMML or I don't care, PyTorch, all these other things. However, the signature of this compute standard model size and compute tailored model size, you could actually be doing a REST call or an RPC call. And imagine if you were, in your real business application, you couldn't load the model into memory. Let's say that you had to put the model on fancy custom hardware, like quantum computers. Like, no joke. We have quantum computer APIs now, I believe, from Amazon. Probably not doing t-shirt sizes, but there are things that quantum computers can do. Google has its fancy hardware called TPUs. You can imagine using FPGAs, some actual custom hardware there, or anything else. So whether or not you load something to memory or you actually have to talk to a remote system in a data center or something like that, it all just works. It's very simple. It's very easy. So again, my thesis, I hope you believe it by now, that Scala with ZIO is an ideal way to architect your applications and then to incrementally add more of these powers from machine learning models. And with that, all I have to say. Thank you very much. Appreciate everything from the ZIO community and of course the Scala community. That's all I have to say. Thank you.
Thank you so much. That was a fantastic talk, and thank you to everyone who took time out of their day to join us here. I think we had two questions. One was about, is TensorFlow ever going to be implemented directly in Scala?
So if I interpret the meaning of the question, here's the answer. The answer is kind of yes, kind of no. Here's what I mean by that. So if you were just using a model, again, like at serving time, you're serving scores, that's something a lot of people do. I do at work daily. Now that just means that someone used TensorFlow to produce a model, and we have this, right now the Java API, and we read in the model and we produce scores. Now, that's the model inference side. If we're talking about learning the model, let's say you are, being amateur or professional data scientist here, TensorFlow itself is written in C++, and there are language bindings primarily for Python. So, and that's what they do at Google. That's how it is. So you're not going to likely see the ability to, like, let's say, easily learn the model, train the model from Scala. If you were interested in, again, staying purely Scala for professional or didactic purposes, something like one of the more popular tools out there is actually, well, there are a couple. Let's say XGBoost, which is kind of a little bit more narrow, but also Spark ML. And you can make really good models using those toolkits, and you can actually be doing data science from Scala itself, Java Scala, yourself. So, but TensorFlow specifically, if you're looking at, if you're interested in making neural network models, there is deep learning for J, which I've used briefly. But that's probably the best answer I can give you.
Great. And then one more that's, I think, a little bit of a Scala and ZIO question. In a for comprehension, are each line in the for comprehension is executed sequentially, and is there blocking there or not?
Got you. So that is an interesting question. It's a good question, and it actually is. There are two halves to that. There's the for comprehension, and then which is from Scala, And then there's, in this case, you saw for comprehensions being used with, building up a ZIO data structure, ZIO, right? So here's the best answer I can give you there is the for comprehension is basically a cool syntax to let you do, well, basically a bunch of flat maps, basically sequentiality. And ZIO uses it to great effect to give you code that's easy to read. And what ZIO will actually give you is, yes, you can do one step followed by another step, followed by another step. Kind of what you read is what you're going to get. Now, ZIO uses fibers. ZIO is not actually going to block threads, like very specifically block threads. You can simulate thread blocking. There's like ZIO.sleep, stuff like that, and won't block a thread. It uses fiber-based, like application fiber-based model to do that. Now, that's ZIO doing very clever, smart things. If you can still write a for comprehension like with a write-based either, Scala 213. And then, for example, if you were just doing using cats and like living inside of an either instead of living inside of a ZIO in your for comprehension, composing it that way, yeah, you could do thread.sleep. Yeah, sure. But you see what I'm saying here. So that's for comprehension is one thing. It's just a language construct. It's a language construct that is used to great effect by ZIO, but they're kind of two different things. So I don't know if you have anything to add to that, Adam.
Yeah, I think you hit it really well of the for comprehension, especially with ZIOs essentially embodying an imperative program within this functional paradigm. So saying do this, then do this other thing, enforcing that sequentiality. But there's never any thread that's blocking along the way. Under the hood, ZIO is using some callbacks to manage that, but you don't have to deal with that. So you get to write that kind of very nice imperative code, but never waste any resources with a thread actually sitting there without work to do.
Yeah, makes sense to me. Cool.
All right.
Well, with that, that's all I have to say. Thank you very much, Adam. I appreciate it.
Thank you so much. This is fantastic.